Alright guys, so today I just want to kind of recap what we need to know so far for circuits and then add in a little bit of the math that goes along with the multiple resistor circuits, um, resistors that are in series and resistors that are in parallel, and right now we're just looking at those individually. We are not mixing them. So first we have our definition of electric current. What we need to kind of keep in mind when we think about the electric current is that it's about the movement of charge. It is about the amount of charge that moves through, um, but it is not a rate at which you're talking about charge building up. As we looked at yesterday, the amount of charge in an electric circuit is the same as it would be if there is no current moving. The point is just how much current moves through a certain point, which is why we talk about flow instead of some sort of excess charge being built up. So just to remind yourself, something that carries an electric current can still be charge neutral. Now, when we talk about energy in any kind of circuit and the voltage, a lot of times we want to think about the voltage telling us how powerful that circuit is, and that is not really the case. When we talk about the electromotive force, it is about electric potential, right? That's voltage, but the actual amount of energy involves the amount of charge that moves through there, and then the voltage. So, for example, your standard AAA battery is 1.5 volts. Your standard D battery is 1.5 volts. Now a D battery can do more work because can run longer and it can move more charge, but it's still the same voltage. At the same time, you have your car battery, humongous car battery. That does not have an incredibly high amount of voltage. I believe your car battery is running about 12 volts. And so the difference there is that that car battery is actually able to move a lot of that charge. It has a lot of charge to move. It can move it quickly. So a car battery can provide a lot more energy, but it's not strictly because of the voltage. It's a combination of voltage and charge. On the other hand, there might be a taser or something that's got 50,000 volts. Um, and in that case, they move actually a fairly small amount of charge, but the humongous voltage rating um, gives a lot of energy, and you can incapacitate somebody. Meanwhile, your electrical outlet is only 120 volts. And so, how can a 50,000 volt taser be non lethal and somebody be electrocuted by a 120 volt outlet in their house? It's because it's the amount of charge and the voltage together which give you the energy. So it is not as simple as just saying voltage in terms of comparing the power output or the energy output of a circuit. And then we come to Ohm's law. Now for Ohm's law, we have the voltage across is equal to current times resistance, and then of course we can rearrange this a number of ways. Voltage is the product of current and resistance. We typically ignore the resistance that is within a wire, but when we look at a resistor, we can determine either the current that's going to be across it based off of the voltage across it based off of the current. And for a single resistor, that's pretty easy for us to do. We have a EMF, we have a resistor, and they're connected. So basically, the most simple circuit that I could possibly draw would look something like this. I've got some EMF, and I've got a resistor. Um, So I've got some resistor connected in here. And it has to actually, it is a circuit, so it has to be connected all the way around, have high potential, low potential, and then there it is, right? So I do have my resistor. This voltage here is the EMF, or the electromotive force, and then I can calculate the current as voltage divided by resistance. Now what we're going to look at here a little bit more in depth is what happens when we are looking at resistors that are in series. So this is the easiest way we want to put these things together, because we can see that if I have resistors in series, all right, I can treat them all as one resistor. So one thing is, and this is kind of goes back to that water analogy, if I've got one long pipe and maybe I have different resistances, different things blocking it up, the fact is that it's one path, and through one path, the current is going to be the same. So for resistors in series, I know that the current in 1, the current in 2, and the current in 3 is all the same current in the entire thing, even if they have different resistances. And one way that I can easily do that is I treat all 3 of these, or however many I have in series, as one equivalent resistor. Basically, they all behave as if they were one resistor. They give us the same current as if it was one resistor with some equivalent resistance. And for in series, that equivalent resistance is the sum of those resistances. So let's just say this was 1 ohm, 2 ohm, and 3 ohms. Well, the total resistance then is going to be 6 ohms. Then we can say, well, let's just go ahead and make this a work through example. Let's say that the voltage on our battery is 12 volts. All right, we have a 12-volt battery. And like I said before, we're going to say R1 is equal to 1 ohm. R2 is 2 ohms. And R3 is 3 ohms. That means that the equivalent resistance is going to be 6 ohms. And we still have 12 volts. And so now I can look at this current and I can say, oh wait, this current that runs through the circuit must be 2 amps. All right. Now the one thing that's kind of missing from this is that each voltage is going to be, across each resistor is going to be different, because the lower resistance is going to require a lower current going across, a lower voltage across it to maintain. Each one of these has a 2 amp current. So we can go back over here, and now that we know that our current, right, is 2 amps, now we can actually calculate the voltage across each of these by multiplying that current. So here the voltage across this resistor is 1 ohm times 2 amps. Well, that's going to be 2 volts. This voltage is going to be 4 volts. I'm multiplying by 2 because my current was 2. 6 volts. And now we can see that 2 volts plus 4 volts plus 6 volts gives us that same total of 12. So basically, and that should always be the case, right? I have a high potential to low potential has a difference of 12. Each time I go across a resistor should be a decrease, and as I go around, I should have the same decrease in voltage across these resistors, gives us the total voltage of the battery. And that is how we solve for our series circuits. We know that the resistances of them total add together. We know that the current in each of them is going to be the same and we know that the voltage across each of the resistors adds up to the total voltage. Now, when we go to resistors that are in series, that is a little bit different. So again, looking at this analogy, you can imagine that if I have, high, on some reservoir up high, and then I've got a change in height, and if each of these is a dam that slows the water but gets some sort of energy out of it as it flows from high to low, you can kind of imagine that if I keep on adding more paths for the water to flow, I'm going to be able to move more water, no matter how much resistance they have, right? I could open a big wide channel. If I add a tiny little sliver on the other side, well, I'm going to be increasing the flow. And so that's what happens with our circuits when we add resistors in parallel, where the path of the flow is going to be through one or the other. That means that when I add them, when I'm including more resistors in parallel, the effective resistance or the equivalent resistance actually decreases. And this gives us a slightly trickier example, but we're going to stick with the same numbers. So we are going to have a 12-volt battery, and we're going to have, 1 ohm, 2 ohm, and 3 ohm resistors. Now, according to this equation, it says the equivalent resistance, or 1 over the equivalent resistance, is equal to 1 over 1 plus 1 over 2 plus 1 over 3. So that means we say 1 over R is equal to 1 over 1 plus 1 over 2 plus 1 over 3. Now, if I'm using a calculator, I can just add these fractions together, but always remember to invert them at the end. If I'm doing this, kind of freehand, I got to get that common denominator, right? So this becomes 3 over 3. Actually, I'm going to need 6 over 6. Then I'll have 3 over 6. And then I'll have 2 over 6. Oh, this is so ugly. 6 plus 3 plus 2 gives me 11 over 6. That's equal to 1 over R. You can double check the math. That means that R equivalent is equal to 6 over 11 ohms. That should make sense because, like I said, every time you add a resistor in parallel, you know that the effective resistance, is going to be less. So I should expect my resistance to be less. The equivalent resistance is always less than even the smallest of these resistors. So here I have 1. This is, almost a half, a little bit more than a half. Well, that should make sense because we're doing that. So we just need to make sure that once we solve for these, we do have to invert it. Hopefully we can double check and just say, is this smaller than my smallest resistance before? And as opposed to the series resistors, what we can say here is, well, if I actually got a voltmeter here, right, I have a high potential on this side and a low potential on this side. So for parallel circuits, they all have the same voltage across them. But see how this current splits up, right, into 3 different paths. The currents actually need to end up adding to give me the total current. And so that part is completely reversed. So when they are in series, they all have the same current and their voltages add up to the total. When they are in parallel, they all have the same voltage across them and their currents add up to the total. All right, so that should help you with your calculations. I hope you guys have a great day.